So, we have studied the power series method of solving differential equations, and we noticed that in the power series method of solving differential equations, we often got solutions that had certain properties, okay. And this property that we will focus on in the next in this lecture and the next lecture is the orthogonality property. Okay. So, suppose we start with Legendre's differential equation, which is 1 minus x square y double prime minus 2 x y prime plus n plus 1 y equal to 0. Now, when n is an integer, the solutions are what are called as Legendre polynomials. Okay. So, they go from infinite series to polynomial, and they are denoted by p n of x. Okay. And these are, so p n of x is a polynomial of degree n. Now, it turns out that these Legendre polynomials are orthogonal, okay, in this sense. In the following sense, they are orthogonal. They are orthogonal in the sense that -1 integral from -1 to 1 p n of x p m of x dx equal to 0 if n is not equal to m. Okay. Now, notice that when n and m, for n you have one differential equation, for m you have another differential equation. Okay. Notice that the form of the differential equation changes as you change the value of n or m. Okay. Whether you say n or you say m, you will get a completely different differential equation, okay. But the solutions are still denoted by this Legendre polynomial. Okay. For example, if n equal to 0, then the differential equation becomes y double prime plus minus 2 x y prime equal to 0. N equal to 1, it becomes prime plus 2 y equal to 0. Okay. So, we notice that these two are different differential equations, okay. They are both homogeneous equations, okay, and the nature of the solutions in both cases are different. Okay. This is a polynomial, the solution of this is p 0 of x, the solution of this is p 1 of x. Okay. This is a solution that is obtained. So, one of the series which converges is your p 1 of x. Okay. So, and according to this rule, you will have that integral p 0 of x p 1 of x dx from -1 to 1 equal to 0. Okay. So, the question we are asking is the following: is there some way to understand when the solutions of a differential equation will give you orthogonal functions? Okay. So, is there something buried in the differential equation that tells you when the solutions would be orthogonal? Okay. I will also mention this that the Bessel functions are also orthogonal, okay, in a slightly different sense. Similarly, the Hermite polynomials, okay, which are obtained when you solve the Hermite differential equation, which is a solution of the harmonic oscillator problem in quantum mechanics. They are also orthogonal. They are orthogonal in a slightly different sense, and we will see it when we come to that. Okay. So, this theory of differential equations and orthogonal functions was done by two people called Sturm and Liouville. And they came up with a theorem called the Sturm-Liouville theorem. Okay. And this is a theorem for orthogonal functions. Okay. Now, according to the Sturm-Liouville theorem, if you have the following differential equation and boundary conditions. Okay. And the differential equation and boundary conditions are given by equal to 0. Okay. So, r y prime the whole prime plus q plus lambda p y equal to 0. Okay. Now, here y is a function of x, p is a function of x, q is a function of x, r is a function of x, lambda is a constant scalar. Okay. So, y prime refers to the derivative of y with respect to x. This is so r into y prime the whole prime. So, if you have a differential equation in this form with boundary conditions, and the boundary conditions are of the following form. K1 plus K2 y prime of A equal to 0, L1 equal to 0. Okay. And this differential equation is valid for A less than equal to x less than equal to b. So, that is a domain of x. Okay. And these are the boundary conditions. So, we have this differential equation with these boundary conditions, and A less than equal to x less than b. So, p, q, r are all continuous in this interval. Okay. So, if we have such a problem, okay, then it is referred to as a Sturm-Liouville problem. And it is called a Sturm-Liouville problem. Again, p of x is strictly greater than 0. Okay. P of x has to be strictly greater than 0. Okay. Now, let us look what this is trying to say. This is saying that this is basically a second order differential equation. So, I can write this as sum of two terms, r prime y prime, okay, and a second term r y double prime. Okay. So, the point is the coefficient of y double prime is r, the coefficient of y prime is r prime. Okay. So, that is the first thing, and then you have some scalar, okay, multiplying some positive number plus some other function, and the whole thing multiplies y. Okay. So, if you can write your differential equation in this form, okay, with these kind of boundary conditions, then it satisfies what is called a Sturm-Liouville problem. Okay. So, the Sturm-Liouville problem, if you have a Sturm-Liouville problem, then the Sturm-Liouville theorem tells you certain properties of the solutions. So, first thing it says that solutions exist for different values of lambda. So, the solutions exist for different values of lambda, and different values of lambda are called eigenvalues, and the solutions are called Eigen Functions. Okay. So, the solutions which are called the Eigen Functions, they exist for different values of lambda, which are called the eigenvalues. Second point is that eigenvalues are real. Okay, so the values of lambda that are allowed are all real numbers. Okay, so you and third property is Eigen functions are orthogonal with respect to weight function p of x. Okay. So, what this means is that integral from a to b p of x. Okay. Now, if the eigen functions are y1 of x and y2 of x dx. So, you can write it in this form. So, this quantity y1 and y2 is equal to 0. So, if 1 and 2 refer to two different eigenvalues. Okay. So, these are eigen functions corresponding to different eigenvalues. Okay. So, this corresponds to lambda 1 and this corresponds to lambda 2, and lambda 1 and lambda 2 are not equal to each other. Okay. Now, notice that the orthogonality relation that it states is with respect to this weight function p of x. Okay. And that and we have to have p of x be greater than 0. Secondly, it specifies the limits a to b. Okay. So, these are points to note. Okay. So, this is the basics of the Sturm Liouville problems, and now there are some more very interesting theorem. This theorem itself is quite powerful, but this theorem is made even more powerful because of some interesting cases. So, and I will write them right here. Suppose you have r of a equal to 0. Suppose you have r of a equal to 0. So, this r is a function of x. The value of this function at x equal to a goes to 0. Then you do not need this boundary condition. Okay. So, you either need this or you need this condition. Similarly, if you have r of b equal to 0, then you do not need this boundary condition. Okay. So, this is an or, these are both or statements. Okay. So, either you can have such a boundary condition where the value and the slope, okay, are linearly related, or you can have this sort of boundary condition. Okay. So, the point is that you should have one of these boundary conditions in one of these forms, okay, in order to satisfy a Sturm Liouville problem. And if you have both r of a and r of b equal to 0, then you do not need any of these boundary conditions. Okay. So, with these conditions we can that means that if you take your differential equation and r of a equal to r of b equal to 0, then automatically this orthogonality condition will be satisfied. Okay. So, now let us look at this and let us compare with the Legendre differential equation. So, the Legendre differential equation is in this form. Okay. We can so if you just look at it, we have to write this. So, if you just look at this Legendre differential equation, what we will immediately conclude is what is p, q and r. So, we have to identify p, q and r based on this equation. So, now notice that minus 2x is nothing but the derivative of 1 minus x square. Okay. So, I can write this as 1 minus x square y prime the whole prime. Okay. So, if I take the derivative of this thing, the first term will give me 1 minus x square y double prime, second term will get me minus 2x into y prime. Okay. So, these two can be combined in this form. The next term is just I can write it as 0 plus n plus 1 y equal to 0. Okay. So, I immediately say that p of x is 1 minus x square, q of x is 0, and r of x r of x is sorry, this is r of x. R of x is this, q of x is 0, p of x is 1, and lambda equal to n plus 1. Okay. So, now if I take different values of lambda, that corresponds to taking different values of n, okay. And if I take different values of n, I get the different polynomials. Okay. So, p n will correspond to value of n, m will correspond to n equal to m. Okay. And notice that r of x has this. So, r of 1 equal to r of minus 1 equal to 0. So, what you do is you look where r equal to 0, and when r equal to 0, x equal to plus or minus 1. So, if x equal to 1, then 1 minus 1 is 0, x equal to minus 1, 1 minus 1 is 0. So, r of 1 equal to r of minus 1 equal to 0, and therefore, you can write this Sturm Liouville problem in this form. So, you can immediately, just by looking at the equation, we can write this orthogonality condition. Okay. So, p n of x, p m of x from minus 1 to n should be 0. So, this theorem, the Sturm Liouville theorem for orthogonal functions, is a very powerful theorem that immediately, just by inspecting the differential equation, we can identify such orthogonality relations. Okay. And it is actually at the very heart of the entire quantum mechanics. So, quantum mechanics, in quantum mechanics, our postulate is that your observables correspond to operators, okay, and the observed value corresponds to an eigenvalue. Okay. Now, you can easily see that if I take this lambda p y to the right, okay, that looks like an eigenvalue equation. Okay. So, it looks like some operator operating on y gives me lambda p times y. Okay. So, the whole it turns out that the entire quantum mechanics, the existence of real eigenvalues and orthogonal eigen functions, okay, the fact that we have Hermitian operators is a consequence of a more general version of a Sturm Liouville theorem, where these can be complex functions. Okay. So, this Sturm Liouville problem is really at the core of all of quantum mechanics. There is one more situation. So, we saw that when r of a equal to r of b equal to 0, then we do not need the boundary conditions. There is another condition when r of a equal to r of b and y of a equal to y of b, y prime of a equal to y prime of b. Okay. So, this is called a periodic Sturm Liouville problem. Okay. So, it is a periodic Sturm Liouville problem, and in this case also we can use the Sturm Liouville theorem. Okay. So, the Sturm Liouville theorem needs either r a equal to r b equal to 0, or r a equal to r b with y a equal to y b and y prime a equal to y prime b. Okay. So, there are, you do not need those boundary conditions in the form that we had mentioned. Okay. So, let us look at some examples now, and we will look at a simple differential equation whose solution you know. So, suppose I have y double prime plus lambda y equal to 0. Okay. So, this is a simple Sturm Liouville form. Now, with the condition that y of 0 equal to y of pi equal to 0 equal to 0. So, if we have this boundary condition, so in this case we can immediately say that the solutions for lambda greater than 0. So, let us take lambda greater than 0. Okay. So, if you take lambda greater than 0, then the solutions are sin mx. So, y m of x is sin mx. Okay. You can put some constants if you want, but I will just look at this. So, sin mx will ensure that it satisfies both these boundary conditions. Okay. Now, if you take this now, according to the Sturm Liouville problem, what we will say is that r of x equal to 1. Okay. So, 1 times y prime the whole prime is just y double prime, p of x equal to 1, q of x equal to 0. Okay. So, this you can verify with the Sturm Liouville problem that this is indeed the case, and so according to the Sturm Liouville problem you will say that 0 to pi. Yeah. So, y of 0 equal to y of pi equal to 0. Okay. So, this can be thought of either as a periodic or a, well, you are given the boundary conditions in any case. So, notice that r of 0 equal to r of pi equal to 1. So, this can be thought of as a periodic Sturm Liouville problem. Okay. So, you can also think of this as this is actually a periodic Sturm Liouville problem. Okay. So, then integral 0 to pi dx. So, the solutions sin nx sin mx, okay, p of x is 1. So, this should be equal to 0 if n not equal to n. Okay, and this is obviously true, because you take sin of nx and sin m of x, sin mx. These if you integrate them from 0 to pi, if n is not equal to m, okay, you can use you can show that this will be sin n plus 1 mx, and you will have sin n minus mx, and those two terms will, each of them will be 0. Okay. So, this is easily verified. So, easily verified. Okay. So, so what we saw is that I mean you can think of this in terms of the Sturm Liouville problem, and the orthogonality relation in this case is easily verified. In more complicated cases, it is not that easy to verify this, but so having the theorem actually helps. So, furthermore, so we saw that what this implies is that, so Sturm Liouville problem or Sturm Liouville problem implies that that in interval a to b equal to b, the Eigen functions are orthogonal. Okay. So, in this interval a less than equal to x less than equal to b, the Eigen functions are orthogonal to each other, and now we can say that any function f of x which is continuous in a less than equal to x less than equal to b can be expanded in terms of Eigen functions. Okay. So, so if these Eigen functions are denoted by y m of x for different values of m, so m equal to, we just denote these various Eigen functions in this way, then you can write any function f of x 0 to infinity some constant times y m of x. Okay. So, what it says is that any continuous function can be expanded in terms of these orthogonal eigenfunctions. Okay. In other words, these orthogonal functions also form a basis. Okay. So, we can go back to the language of vectors and we can say that these are linearly independent, they form a basis, okay, and any function that is continuous in this range can be expressed as a linear combination of these eigenfunctions. Okay. So, what we have done is we have gone from the language of differential equations to a language of vectors and bases. Okay. And we could do this because of this Sturm-Liouville theorem for existence of orthogonal eigenfunctions. And now, if you recall the postulates of quantum mechanics, one of the postulates of quantum mechanics states that, so I will just write recall postulate of quantum mechanics. Okay, one of the postulates, okay, is that for every physical observable okay, there exists an operator in Hilbert space okay. So, for every physical observable there exists an operator in Hilbert space whose eigenfunctions, eigenvalues are real and correspond to values observed in measurements. Okay. So, and so there exists an operator in Hilbert space whose eigenvalues are real and correspond to values observed in measurements and whose eigenvectors for different eigenvalues are orthogonal. Okay. So, if you take two different eigenvalues, the corresponding eigenvectors or eigenfunctions are orthogonal. Okay, I should say eigenfunctions. So, whose eigenfunctions for different eigenvalues are orthogonal to each other. Okay. There is another statement, there is another part of this, if we have degenerate eigenfunctions. Okay. So, if you have one eigenvalue and you have multiple eigenfunctions, okay, they can be chosen to be orthogonal. No? Okay. Now, this is a very powerful statement. It says that if I take any physical observable, okay, and I see that it has degenerate eigenvalues, okay, then I can choose these degenerate, I can choose the eigenfunctions to be orthogonal. Okay. So, this is a very powerful statement, and the fact is that this is true for every physical observable. So, for each and every physical observable you can do this. Okay. And this postulate of quantum mechanics was finally arrived at by Dirac, but he used some of the properties of the Sturm-Liouville problem in order to arrive at these postulates. And what I want you to appreciate is that the idea of orthogonal eigenfunctions is something that is very, very central to all of quantum mechanics. Okay. So, this is one of the most fundamental postulates of quantum mechanics. It tells you what is it that you measure in quantum mechanics, what does it correspond to. Okay. Okay. So, when we do such a basis function expansion, then what is the value of a m of x? What is the value of a m? Okay. And you can show this, that a m is equal to integral f of x y m of x, okay, p of x dx divided by 1 over y m square, okay, where this is from a to b, where y m is equal to integral p of x y m of x y m of x dx from a to b. Okay. So, this completes the basis function expansion, okay. And what we have seen is that if you have orthogonal eigen functions, they can be chosen as a basis. Okay. So, you can expand any function that is continuous in this limit from a to b in terms of this basis, and this is connected to one of the fundamental postulates of quantum mechanics, which says that for every physical observable there exists an operator in Hilbert space whose eigenvalues are real and correspond to values observed in measurements, and whose eigen functions for different eigenvalues are orthogonal. If we have degenerate eigen functions, okay, that means many eigen functions corresponding to the same eigenvalue, then you can choose them to be orthogonal to each other. That means, in other words, you can say that eigen functions of any physical observable okay, and when I say any physical observable, I mean eigen functions of operators corresponding to any physical observable can be used as a basis. Okay. And this is one of the most important theorems in quantum mechanics, okay, or it is actually a postulate of quantum mechanics that you can use eigen functions of any physical observable as a basis. Okay. So, you can write your general wave function as a linear combination of eigen functions of Hamiltonian operator or the momentum operator or the position operator, whichever operator you want, okay, and this is generally true. Okay. So, we have seen the Sturm-Liouville problem, and we have seen how the nature of a differential equation can tell you whether you can have orthogonal eigen functions as solutions. Now, a very important and very widely used example of this is in the Fourier series and the Fourier transform, and that will be the topic of this lecture and the next few lectures. Okay. So, first we will start with the Fourier series. Okay. And in this I will try to motivate it from the perspective of a Sturm-Liouville problem of differential equations. So, suppose you had a differential equation y square y double prime plus ky equal to 0, and if you want choose this as k square. So, k square will ensure that the coefficient of y is positive. Okay. So, suppose you had such a differential equation, then you can easily show that y is equal to sin kx. These are examples of solutions. Okay. So, these are examples of solutions of this differential equation. Now, if you think of this as a Sturm-Liouville problem, then what you will say is that of x is equal to 1, okay, because and r of x was equal to 1 for all x. Okay. So, r of x is 1 for all x. So, we can formulate this this as a periodic sturm Liouville problem. Okay. And we can take any period and we can formulate it as an appropriate periodic sturm Liouville problem. What we will do is we will formulate it as a periodic sturm Liouville problem. We will notice that R of minus L is equal to R of L equal to 1. Okay. So, what we will do is we will formulate it as a periodic sturm Liouville problem between minus L and L. Okay. So, so we look for solutions satisfying y of L equal to y of minus L, okay, and same with the derivatives. Okay. Since R of minus L is equal to R of L, we can choose solutions that satisfy this. Okay. And now, if you choose solutions, then you can easily show that if you want to satisfy these boundary conditions, the general solution is A sin k x plus B cos k x. Okay. And if you want y of L equal to y of minus L, then you will get that you will get A sin k L plus B cos k L is equal to minus A sin k L plus B cos k L. So, sin of minus k L is minus sin k L, cos of minus k L is just cos of k L. So, you get this, and what you immediately see is that 2 sin k L equal to 0. This implies k is equal to n pi by L, okay, where n is equal to n is any integer. Okay, so mathematically we can say that any k has to be n pi by L, okay, and this will satisfy this sturm Liouville problem. This will satisfy the conditions of the sturm Liouville equation. So, then you can say that you can write the general solution is equal to some constant plus another constant times cos. Okay. So, what we did was we wrote it in this way, so that it becomes very clear what the conditions are. Okay. Now, k equal to n pi by L. So, if k is n pi by L, we can think of this as y of n. Okay. So, I can write my differential equation as y double prime plus n square pi square by L square y is equal to 0, and this is a differential equation. So, lambda is here, your eigenvalue is here, and y n is equal to a okay. So, corresponding to any n, you can have either a solution of sine or you can have a solution of cosine. Okay. Now, we can choose either one of these as the eigen functions, because sine and cosine are related by a simple shifting. So, we can choose either one of these as the eigen functions. So, depending on your choice of boundary conditions, you can choose either of these as the boundary condition. So, suppose you want that your wave function is 0. your y of, suppose y of L equal to y of minus L equal to 0, then y n of x. Okay. So, when you put x equal to L, this term will give me 0, this term will not give me 0 in general, it will not give me 0 in general. So, then it is best to choose y n of x as sin n pi x by L. Okay. So, if you have this y of x go to 0 at these boundaries, then you choose sin n pi x by L, and this is exactly what is done in the particle in a one dimensional box problem in quantum mechanics. On the other hand, if you have some conditions on the derivative of y at the boundaries, then you choose cosine functions. Okay. So, now either of these can be used as infinite series, or you can use a combination of these as the general solution. Okay. Now, so then the Eigen functions are sin pi x by L, sin 2 pi x by L, and so on, or cosine of pi x by L and so on. Okay. So, either of these cases works equally well, and we can choose these as eigen functions, and then the Sturm-Liouville theorem says that integral from minus L to a plus L sin n pi x by L sin m pi x by L equal to 0 if n is not equal to m. Similarly, for the cosine, when one can also write for cosine, okay. Now, interestingly, we notice that if you take a mix, if you take interestingly note that integral minus L to L sin n pi x by L cosine of m pi x by L equal to 0. Irrespective of whether you take n and m the same or different, whether you take them as the same or you take them as different, this integral will go to 0. So, in a sense we can take this entire set as a set of orthogonal functions. Okay. So, since sines and cosines are orthogonal to each other, we do not need to choose only sines as orthogonal functions or only cosines, we can choose a combination of these, and this is what is done in the typical Fourier series. Okay. So, in the Fourier series in the Fourier series you write any function f of x as a linear combination of sines and cosines. So, you write n equal to x by L or a n cosine. A n, the typical notation is a n is used for the cosine series and b n is used for the sine series. So, n goes from 0 to infinity. We deliberately eliminated the negative values of n, okay, because it turns out that those, when you take negative n's, it's just a simple multiple of this. So, cos of minus n pi x by L is same as cos of n pi x by L. Sine of minus n pi x by L is minus sine. So, those are linearly dependent functions. So, we do not need to take them in this basis expansion. Okay. Now, what is done typically is that you take the n equal to 0 n equal to 0, you have a 0 cos of 0 is 1 and b 0, that term will be 0. So, this term is taken out a 0, okay, and for convenience you put a factor of 2. Okay, so this is added for convenience. Okay, so you define your a 0, okay, with this 2 factor, okay, and then you write plus so you write your series in this form. So, and it will become clear why we chose to do it this way. If you write it this way, then the question is what are a n and b n given by, and you can show that a n is equal to, okay, a n is given by 1 by L integral minus L to L, okay. So, there is 1 by L, and what you have is cos n pi x by L times f of x dx, okay, and b n dx. Okay. Now, notice that that if you put n equal to 0, then a 0 is just integral minus L to L f of x dx divided by L, okay, and if you just do integral from minus L to L of f of x, okay, that will just be integral of this right hand side from minus L to L, okay, and you can show that indeed will give you a 0 times L, okay, because all other terms will vanish. So, what you will be left with is a 0 by 2 times L, okay. So, that is the reason why we put this 2 factor here. So, if we put this 2 factor here, then the a n definition, you have a unique definition of a n in this way. So, this definition is valid for all n, okay. In this case you can check that b 0 will be 0. So, this is valid for n equal to 0 also. So, all this is valid for all n. And including n equal to 0. Okay. So, in other words, a 0 equal to 1 over L integral minus L to L f of x dx. Okay. So, a 0 is just the area under this function f of x divided by factor of L. Okay. Now, this is a general basis function expansion, and what we see is that this is, you can expand any function that satisfies the boundary conditions in terms of this basis, and the boundary conditions are that f of L equal to f of minus L. Okay. So, f of L should be equal to f of minus L, and any function that satisfies these boundary conditions can be written in this basis form. Okay. Now, suppose f of x plus 2L equal to f of x. Okay. In other words, x is a periodic function of period 2 pi. Okay. So, if f of x is a periodic function with period 2L, then we notice that sine of n pi x plus 2 l divided by l is equal to sine n pi x by l, and cos is equal to cos of n pi x by l. So, in other words, this sin n pi x by l and cos n pi x by l are also periodic functions. Okay. So, that means each of these terms is periodic with period 2l, and therefore, this function that you are expanding will automatically be periodic with period 2l. Okay. So, to come back, what we meant is that when we wrote this expansion, this was only valid for minus l less than equal to x less than equal to l. So, it was only valid in this range, okay, because our solutions were only valid in that range. Okay. But if your function is a periodic function, if what you are doing is actually a periodic function, then solutions are valid for all x. Okay. So, the point is we started with this expansion which was only valid for minus l less than equal to x less than equal to l, and then we said that if your function was periodic, then the solutions are valid for all l. Okay. If your function is not periodic, then it is only valid for this range, but if your function is a periodic function, this is valid for all x, and this is what is used to motivate the Fourier series. Okay. So, this is called the Fourier series for periodic functions. So, you can write if f is a periodic function of period 2l, then you can write it in the form of this Fourier series. Okay. you.